1986, and he started out in Middle Lake College, as we chatted about earlier here, a nice little detour on his way out west. Some of the projects that he has been and or will be working on are glaciation in the Sawtooth Mountains, sedimentation on the eastern Snake River Plain, hydrology, surficial and subsurface sediments in the eastern Snake River Plain. So, to say that Glenn is familiar with a lot of the geology of this part of the world is something of an understatement. He says that his research interests are principally in the application of quaternary geology, so very young geology, and geomorphology to paleoclimate investigation. So in other words, what can you see in the rocks today around us that inform you about what this place looked like 10,000 years ago, 100,000 years ago, and beyond? And Glenn will be touching on some of that here this evening. He's very well published, has a long list of graduate students, and in fact he was trying to handle one of his graduate students here just as soon as he walked in the door. So without further ado, I'd like to ask you to join me in welcoming Glenn Thackeray.
Okay, well, thank you, John. Is my voice coming through the speakers? I can't really tell. Okay. I'm not used to using a microphone because usually I talk loudly enough to fill the room. But it's nice not to have to talk loud to fill the room. So anyway, thanks, John, for the introduction, and thanks to geologists at Jackson Hole for having me over here. I think there are a lot of these types of organizations in a lot of towns, and the enrichment that these organizations bring to towns like Jackson is great, and people can tap in and tap out as they see fit, and it's just a great thing. And I love to see and hear about the variety of presentations they bring, and everything from extremophiles to activity, deep activity under the Yellowstone hotspot. And I'd like to thank all of you for coming in tonight. I can see out the windows here that it's still a very nice evening out there. And I know sometimes it's hard to go sit inside in a dark room on a nice evening. So I'll try not to talk too long. And I'll try to make sure that the visuals up here are worth being inside for. So there we have it. So on the screen, of course, is a winter view of the Teton front, and this is Great Glacier habitat. It is now, even though they're pretty small in most cases. It is Great Glacier habitat. It's a very high range that captures a lot of precipitation, and in various ways that'll sort of bring this topic around how glaciers work. It's the location of the Tetons, and it's the elevation of the Tetons, and especially the climate of the Tetons, that allows these glaciers to survive here, and in some cases to actually thrive quite well in the current environment. So anyway, what I want to do tonight is I want to go through a fairly lengthy introduction. And one of the things that I want to do before I really start talking about the glaciers of the Tetons is I want to talk about how glaciers work. And we all kind of know that there are these masses of moving ice usually in the mountains, at least at our latitudes, and that they used to be a lot bigger than they are now. 20,000 years ago, the glaciers were filling the valleys of the Tetons and coming out to the range front and beyond the range front in a few places like Denny Lake. And then a large ice mass covered much of Yellowstone was coming down to this area. So they used to be much, much larger. And in looking at glaciers of the past, and looking at, 60 years might sound like a long time to geologists, very short period of time, but looking at glaciers over some time period in the past, be it 20,000 years, be it 60 years, tells us a lot about how climate has changed through time, and climate changes on all sorts of time scales. I won't get much into the controversial side of climate change tonight, mainly because I don't need to. There's nothing controversial here. But I'm really quite fascinated by the notion of past climates and how they've influenced the landscape, and how what we see today, in many cases, is a result, the details of the landscape at least, are often a result of what has happened over the last couple million years, that quaternary period of geologic history that John mentioned. So before I go further, backwards to down there, okay. I want to make sure that I acknowledge a student who did a lot of the work on this project. Hazel Reynolds finished a master's degree in our department a couple of years ago. I thought it said it down there, I guess it doesn't. 2 years ago, and her thesis was essentially this project on studying the recent variations of the Teton glaciers. Hazel was a real trooper on this project, and I want to give her particular kudos. She is not a mountaineer, and she is from Maine, from low country Maine. She went to school at the same school I went to in Wisconsin, Lloyd College, first graduate student I've ever gotten out of there. If you know southern Wisconsin, you know that it's flat, and there's not a lot of topography there. And she worked on a glacier in Alaska, but it wasn't really high in the mountains, it was kind of down in the lowlands. And she came here, she really wanted to work on modern glaciers. Well, to get to modern glaciers around here, you have to get into the mountains, and Hazel was definitely a trooper, not a rock climber whatsoever. There were certain glaciers she would have liked to have gotten to, but never did. She did a great job of putting this project together and sort of toughening up in the mountains. And now she's working for mining companies in northern Nevada and doing very well. Okay, so here is the Schoolroom Glacier. I think I have this particular photograph in here 3, maybe 4 times, and there's a good reason. For one thing, we can see the whole Schoolroom Glacier. We can see people in front of it. And one of the things about the Schoolroom Glacier is it's a glacier that people can get to quite easily in the Tetons. It's nothing technical getting up there. It's a long hike, and you can get to this vantage point with 8 or 10 miles of beautiful hiking. And so this is one of the 13 or 15 or so glaciers that still exist in the Tetons. And it's called the Schoolroom Glacier, I believe, because it has all the features that glaciers typically have, all in one sort of nice, compact space. And so for years, apparently, people have been bringing students to the Schoolroom Glacier. It's like going to the schoolroom for glaciers. So what is it about glaciers that's fascinating? And for me, I don't know where it started. I've always been fascinated by ice in whatever form. I grew up in the Midwest, in the upper Midwest, in the very snowy 60s and 70s. So I grew up around very, very deep piles of snow. You know, there'd be 4 or 5 feet of snow piled up in the backyard in some winters. It was spectacular. I learned to love snow. I played hockey and for a lot of years, so I'm fascinated with what happens when you bring an ice skate across the ice. And it's just that solid form of water that is sort of on that ragged edge of being water. And there's something fascinating about that. I'm always paying attention to ice. When the little river in Pocatello starts freezing over in the winter, it's almost like plate tectonics. It's plates of ice going under other plates. And I'm always going down there and watching that thing freeze up and wondering whether it's skatable and so forth. So I've always been fascinated by ice. And when we talk about glaciers, we're talking about masses of ice, and again, in our latitudes, typically in the mountains. And there's some very important aspects of these glaciers. For one thing, they're in the highest, most shady, most snowy parts of the mountains. So they're kind of fascinating in that way because they're in fascinating pieces of the landscape. And then they're very important agents of the landscape. This is a pretty small glacier right now. It's been larger in the past, and a lot of the high country landscape that we see in the Tetons is a result of that carving action of glaciers. The other thing about glaciers that's quite important in the broader picture, does it matter to somebody in Hobart that these glaciers are in the Tetons? And the answer is yes, it does. And here's why. Glaciers they're masses of ice that are formed from snowfall, and they form where more snow falls than can melt every year. So you have an excess of snow on a year-by-year basis. That's where we get glaciers, a very simple equation with some variability that I'll talk about in a little bit. And so these things are taking that snowfall, converting it to ice, and holding it for some number of years. In the case of the Spoon Glacier, it may take 3 years to a decade for that ice to move through, to come to the bottom of the glacier and melt, and eventually go into the lake, but eventually flow out of the lake and down through South Cascade Canyon and then out into Jenny Lake. So there's the glacier slows down that water. So it's atmospheric water falling as snow, getting compressed into ice, flowing slowly down slope, getting released into melting, and that's a long-term storage. Even a decade is a pretty long-term storage. And of course, in this part of the world, we're very much tuned into snowpack. Snowpack the last couple of years hasn't been very good, except maybe at Tardy, I suppose. And we ski at a small ski area down near Pocatello, and the snow wasn't nearly as good this year. But we're very keenly aware of snowpack, not just for skiing, but for irrigation and for how much water is going to be in the river in September and all those sorts of things. And the snowpack more or less comes and goes every year. Pile up 50 inches of water equivalent of snowpack in the Tetons. Well, most of that melts and goes away, unless it's a very snowy winter and a very cool summer. So the glacier is holding on to that for longer. And the other thing that glaciers do in terms of water supply, they're a bit contrarian, if you will. In a cool, snowy year, more of that snow gets held and gets compressed into ice and gets stored. So when you don't need the water, the glaciers are holding it back. In a hot, dry year, the other extreme, not much going in, and that glacier is going to release more of that water. So they're a buffer in the river system. They're holding that water, and they adjust sort of the way that we'd like them to. And that's a pretty neat thing. Now the glaciers in the Tetons are pretty small compared to the overall snowpack, so the volume effect isn't great, but glaciers in general are very important for water supply. All right, so enough of waxing sentimental about glaciers. Let me tell you a little bit about myself. As with many geologists usually don't like to stay in one place. And geology is this great excuse to go places. And somebody told me when I was in high school, if you like to travel, geology is a great field for you. I said, okay. And I was interested in it for a number of reasons, but I worked in of the climate of wherever they're trying to exist. We like to of the West Coast. All right. So, and I had to throw this in. This is Idaho. The closest thing we have to glaciers in Idaho, I'm sorry to say, although these are fascinating features, it's a whole different story. This is a rock glacier. There is the ice in there. This flows like a glacier, but the ice is, it's layers of ice as far as we know. Layers of ice within a pile of rock debris. It gets insulated in there, it survives, and there's enough ice in there that it flows like a glacier. And these form in the very shadiest spots. In the Lemhi Range, I had a student who worked on that, graduate student worked on that a few years ago, and they find, you can find the shadiest spots in the Lemhi Range by finding those guys. And there are a few other things there as well, but that's the only thing we have surviving in Idaho. There aren't any clean ice glaciers where you can actually see the ice. Interestingly, that glacier is growing and it's knocking over this forest, and the trees in that forest are about 600 years old. So these are not as closely related to climate as clean ice glaciers. Quite a fascinating feature. I want to step back in time to 20,000 years ago. Pleistocene North America looked like this. Canada was covered by ice. Some people would say it's still covered by ice, but it's touched by this big someone's hockey up there. And ice came into Illinois and Indiana and across Michigan, and the landscapes that I grew up in, and then ignored the glacier stuff right in there. And then we had extensive mountain glaciers throughout the Rocky Mountains. Yellowstone is up here, and various mountain ranges of Wyoming are up here. And, big ice caps on the coastal mountains and up into Alaska and all that. So spectacular. Why was this? Because the summer temperatures especially were cooler. Not frigid, probably 50 to 60 degrees Fahrenheit during the summer. That's what's required, and probably a little bit more precipitation. That's what's required to cover half the continent with ice. All you need to do to wipe out the major cities in North America is cool climate down by 20, 30 degrees in the summer and grow an ice sheet. That's what I'm telling you. All right, and closer to home, this is the Teton Ranges right here, under a lot of ice. Jenny Lake is this green dot. This is from a study by Joe Lutardi and Ken Pierce on the ice cap that covered Yellowstone. Yellowstone was almost completely covered by ice, and this would be the Beartooths up here. And all these numbers are the numbers of thousands of years ago that the glaciers ended at those various locations. And so this was this large in part because it was colder, but again, not much colder. And average mean annual temperature about 6, maybe 8 degrees cooler Celsius. Average temperature across the year. Not a ton colder in that sense, but that's what causes an ice cap to grow on Yellowstone and to extend down into Jackson Hole, and for much of the Tetons to be covered by ice. And about 14 to 15,000 years ago, the ice was at that moraine hill that holds in Jenny Lake. So just to give you some context. So 15 to 20,000 years ago, this area saw a lot of ice, and then it all went away very quickly as the climate system shifted around. All right, I'm going to jump quickly over this because I'm kind of blabbing on. In terms of the Pleistocene, I've been working in these two locations, and this is sort of lead into the Tetons. These are areas that are very, very wet. New Zealand and the Olympic Peninsula in Washington, very wet mountains. I've talked about them already. And the question is, do these glaciers behave like most other glaciers? The answer is no, they don't. And there's a very specific reason. So, we see lots of gravel and lake mud, and we do all this real work. This is sort of my, for the geologists in the room, these are to demonstrate my bona fides in geology. We actually do sediment work and all this stuff. So there's a lot of work put into this one clip of stuff. And then on the Olympic Peninsula, we're talking about systems with lots and lots of gravel. The most important thing is that these are in very wet places, and for those glaciers to grow big, they have to have a lot of precipitation. And so, so I call these wet glacier systems, and most people would. There are various classification schemes for glaciers that we don't need to get into. I just call them wet. Makes sense. These grow at strange times. They weren't at their biggest when Canada was covered by ice. They were at their biggest at an earlier time. So they behave a little bit differently. Biggest when it's cool and still lots of moisture coming in. When the temperatures are at their coldest, it's drier, and so these glaciers shrink. So they kind of are the contrarian glaciers, and I'm a bit of a contrarian scientist, and these are contrarian glaciers, so they fit me very well. So, very importantly, it's not just temperature that causes glaciers to grow and shrink. We have to incorporate the precipitation side. So finally, I'm going to come to the Teton Glaciers once again. So there's that picture of the Schoolroom Glacier, and here's what we did. So there are, I don't even know the number anymore, 13 named glaciers existing in the Tetons. Let's see if we can count them up. 5 around Mount Moran. Peterson Glacier seems to not be a glacier anymore. We've sort of written its epitaph, I suppose. It wasn't much of a glacier 50 years ago, and it's much smaller now. If there's any ice there, it's completely buried under rock. It's become a rock glacier, in fact, like the one I showed you. Around the Grand, there are three of the largest glaciers, of course. That's 8, 9, and the Skurum would make 10. I thought there were more than that. But anybody know of any others? Maybe we're missing a couple here.
They say there's 12.
12. And see, that's the number that's sticking in my mind. 12, 13. Anyway, there might be a couple more there, but if there are, they're quite small. All right, so our goal was to go back 50 to 60 years in time. There's a specific reason we're limited to that, and determine how the glaciers have changed. We're only going to talk about the area of the glacier, not the thickness, so we aren't talking about ice volumes. There was a great study by a graduate student at Wyoming at the time named Jake Edmonds, and he did a much more sophisticated study of the Teton Glacier and could get at volumes because of how he worked the analysis. And so that was a much more detailed study. This study is broader and gives us more of the details in between, but we have to deal with the area because we're looking at it in old photographs. So, determining the major climatic influences. So the question is the Teton Range wet? And the answer is, well, not really. It's a continental climate, but it's not. And if you look at this map, this is a precipitation map for the United States. There are the Olympics. That's why there are glaciers there. Look at that purple color there. Cascades. The Coast Range is very, very wet. And this is, of course, is the dry interior. So the oranges are, the yellows are 20 to 30 inches of precipitation. We're getting down to the reds less than 5. That's probably Death Valley and so forth there. But, and so what we see is a dominance of blue colors, lots of precipitation on the west coast, greens in the mountains of the western U.S., except a few places, the Bitterroots, and in the Tetons. There are lots of blues in the Tetons. So the Tetons, for where they sit in the continent, and Yellowstone as well, for where it sits in the continent, these places are pretty wet for where they sit in the continent. They aren't a truly continental climate. The reason is the Snake River Plain is a big funnel. So when the storms come across the, come from the west, and you guys are hoping for snow at the ski areas, you're hoping that that moisture isn't going to come across like this. You're hoping it's going to come up the Snake River Plain and slam into the backside of the Tetons, dump on Grand Targhee, and some of that gets dumped into the Tetons and comes over this side and feeds your ski areas, and sometimes maybe not so much, including the early winter this year from what I heard. So anyway, it's a wet place in the context of where it sits. It's the wettest place in this part of the continental interior. So yes, it's fairly wet. And so this is a place, if it was just a dry place, I wouldn't bother, but because it's wet, I'm interested in the glaciers. Cool and snowy highlands, 60 to 80 inches of mean annual precipitation. That's pretty self-respecting precipitation. And then there are those high peaks. High peaks do a great job of shading some of these snow accumulation areas and keeping the melting down on those glaciers. And as far as I can tell, those peaks aren't going to go away anytime soon. What did we do to do this? Well, these glaciers are pretty hard to access, and if we look at them in 1 year, we have an observation of 1 year. It's hard to tell change from 1 year, and a master's thesis doesn't last very long, a couple of years, and so we had to be able to go back in time. What we did is we went to air photos. One of the great the scientific and government communities in the United States have done a number of great things over time. Put a lot of stream gauges in so we know the hydrology of rivers around the U.S. for years and years and years, decades. Another thing that was done is a lot of, going back into the 40s, the agencies like the U.S. Department of Agriculture, the Park Service, have had aerial photographs flown. These are formal aerial photographs, not just taken out the window of a plane, but a camera mounted in the bottom of an airplane, flying defined routes, very systematically photographing the landscape. It's done for forest management and all sorts of things. And fortunately, but not everywhere, but fortunately, some people have seen fit to keep the old photographs around. And sometimes you talk to somebody who manages the forest and say, well, it's out of date. We don't need that anymore. And we take that into our geology part. We don't want to let those things go. And various agency offices are starting to realize, hey, this is an incredible resource. We need to preserve these things. So from various places, Hazel Reynolds was actually able to find air photos stretching back to 1946 of the Tetons. We can look at the Tetons in 1946. To use them, and then there's some satellite imagery, and this is all done in a geographic information system, which is a computerized way of keeping track of geographically oriented data. And so she went through those air photo archives, and there were about 20 sets of air photos that she could access online or at an office in Salt Lake that preserved a bunch of them. Park Service had some. And out of those, there were about 10 that were appropriate. The key is to understand the size of the glacier. We have to look at it at the end of the summer. When all that melting has occurred, that's when we want to look at them. So they can't have cloud cover. They have to show the glacier well, and you'll see examples of these. So it's mostly based on air photos, or recently some satellite images. Weather records. There are long weather records at low elevations, very little measurement at high elevations. The SNOTEL sites that monitor snowpack are a great addition, but they don't go back very far. And there are very few high elevation stations. There's one in the Tetons run during the summer over the last few years, I think by the University of Utah. And mostly we have to use low elevation climate from Moose, from Alta, from Driggs, and extrapolate that up several thousand feet into the mountains. And that's fairly error prone. So, and then we went out in the field, and especially Hazel and her field assistants did, and mapped the size of the glaciers, the shape of the glaciers, and mapped their features, so we kind of understood how they were behaving in the long term. All right, so let's talk about the Schoolroom Glacier, and I'll focus on this one because it's kind of the most interesting of the bunch. And Schoolroom Glacier, this is Hurricane Pass right here. There's the trail going down the Alaska Basin on the west side. Schoolroom Glacier is just off the lip. This is a cliff right here. So this is a vertical air photo, and this is the cliff that you'll see that you've seen in the background of the picture. That picture I've been showing what we understand from the climate records. All right, so there's two. A signal of diminishing ice area, and we're seeing that over time. You'll see that in the graph in just a moment. But we're also seeing times of ice growth. That's the good news part of the story. All right, we did the same for the triple glaciers on the north flank of Mount Moran. Mount Moran, the peak is somewhere right up in here. That bit of sandstone, and it might be right there, I'm not quite sure. And we did the same thing there. I won't go through this. One of the things about the triple glaciers is there's a lot of rock debris on the ice. Kind of hard to tell where those edges are, but we're pretty confident we got it fairly well figured out. And there's a lot of shadowing in here, so it may not look like those lines are terribly accurate, but a lot of time spent outlining these glaciers on the computer screen. All right, so that's what we're using for data, and here's the result. So, looks like spaghetti, and there's good reason for that. These are the glaciers that we looked at, and in fact, those are the triple glaciers, the Skillet and Falling Ice glaciers on the south flank, the sort of east flank and south flank of Mount Moran, and then the Schoolroom Glacier. So we looked at all those photographs of the Schoolroom Glacier, and here's what it means in terms of area. We sort of normalize this. We do it we compare it to an average in essence, and just to get the numbers cleaner and make one glacier comparable to another. The yellow line, the dancing yellow line, is the Schoolroom Glacier. Diminished very rapidly into the 70s, grew into the, I guess that would be the early 80s, and then shrunk dramatically into the mid-90s, grew into the early 2000s. Anybody want to speculate why that glacier, who was here in the late 90s? Who remembers the 1997 flood of the Snake River? It was a big one. It was an amazing snowpack that year. A series of very snowy years there. And it was just after I moved to Idaho, I thought, wow, this is great. And little did I know that wasn't typical, but it was a series of great snow years. And guess what? A lot of snow got added to the Squirrel Glacier, and it grew a bit. And then it shrunk again to 2006. That's a very small. These all come together just because we chose 2006 as the starting point. And then in the last, we haven't been there in a couple of years, but by 2011 it had grown a little bit again. And that's where we have some on-the-ground observations. Now I'll come back to that in a little bit. So that's a variation, and there are various times when a couple of the triple glaciers grew. Sort of during this time, and notice that the date of the photograph is different here, so we don't have direct overlap. There's a little bit of a problem there. West Triple Glacier showed a big growth in that time, and so what Hazel did was she summarized periods of retreat, periods of advance, and periods of advance and retreat are of course overlapping there. But we're especially interested in periods of advance. You know that the climate has warmed up some, but why was it advancing? And so there's going to be two more graphs, and then I'll stop on the graphs. Geologists are great at thinking in graphs, thinking of the world in graphs. And I know not everybody does the same thing. At least I hope not. The world does not need to be reduced to a graph. But here are some weather records. Alta, Wyoming, Moran, and then we have snow-tell sites at Grassy Lake to the north, Phillips Bench to the south, I believe near Teton Pass. And then again, our times of growth and retreat. So there are times when temperature at Alta on the west side is warmer. There's a cool period in the 70s, and then it warmed up again from there. You see a general trend at Moran upward. I could make a line through there about like that, but with a lot of variability. Of course, we know that the climate, the weather from year to year is very, very variable in these areas. And then the snow-tell sites are very recent time there. And so that's temperature varying quite a lot. And we can find a period of glacier growth during a fairly cool period there. And this is a visual way of saying, yeah, temperature is important here. And I want to go that way. So here's precipitation. Precipitation is highly variable as well. And again, now we have Alta, Wyoming, and Moose, Wyoming, where the good precipitation records are, and Moran. And we can see in this period, it was this period of glacier growth, it's a period of fairly decent precipitation. There was a period back here where we don't see growth, maybe because we don't have photographs during the right sequence of years to actually pick it up. So just because we don't see it doesn't mean it's not there. And then the big precipitation years of the late 90s caused glacier growth on most of the glaciers, as we would expect. So the glacier response is some combination of response to the temperature and to the precipitation. So if it's warm and dry, the glaciers are going to shrink. We know that pretty well. If it's cool and wet, the glaciers are going to tend to grow. And this shouldn't be surprising. But I tell you, I have a really tough time convincing people in the glaciology world that we have to pay more attention to precipitation, because there are a lot of glaciers, if you shut off their precipitation, you can keep it as cold as you want. They are going to shrink because they're accustomed to, if you will, they're accustomed to that enormous input of precipitation. So the amount of snowfall is very, very important. Now, interestingly, so this is just comparing wiggly lines to wiggly lines, and we have to be a little careful of that. I just want to make the point that we did a lot of statistical analysis. I won't bore you with it, but I will tell you about some of the results. It's kind of cool. We also did some modeling. There's a fellow at the INL named Mitch Plummer, whose day job is a groundwater hydrologist. He studies groundwater flow and models that. His avocation, what he's actually trained in, is in modeling glaciers. So he has a glacier that takes weather records and determines how much of the snow should melt. It's a computer-based model, so we use that as well. I won't talk about that, but we did quite a lot of analysis here. So after a series of cooler, snowier years, glaciers tend to grow. Not surprising, but it might be surprising to the snowier part. Might be surprising to some people who work in the field. Some very smart people. seem to ignore that, or seem to forget that a lot. Spring precipitation. If we average spring precipitation over 4 years, here's the most interesting part. It's not winter precipitation, and it's not summer temperature. Those come into play. But spring precipitation seems to be the strongest correlation to glacier growth, and shrinkage. So a series of years with a lot of spring precipitation, the glaciers will tend to grow. So why spring precipitation? Well, it could be a number of things. At those elevations, in a wet spring, it's not a wet spring this year, it wasn't a wet spring last year, but there were 3 years there where it was very wet in the spring. 9, 10, and 11, 2009, 10, and 11 were very snowy springs. And there was snow added at high elevations in some of those storms. If it's rain, the game is up. The ice will start to melt. Cloudiness may come into play, just knocking back the sun. Spring day like this in 2013 compared to a spring day 2 years ago in 2011, a lot more melting today than an equivalent day back then. Cloudiness may, precipitation comes with cloudiness, so the glaciers may just be in shadow more than in sun. Lower temperatures in the spring might also play a part. And what I think is that spring weather, it's not just that it's wet and cool, it's that it's wet and cool sometimes till July 1, sometimes to July 15th, right? And sometimes we have years like this, so you compare that wet June 2 years ago to this one, the melting season this year, with all this sunshine out there, is going to be a much longer melting season. It may not be that hot summer, hot a summer, we can hope it's not, if we don't like heat, but like I don't, but it may not matter how cool that summer really is, or how hot that summer really is, it's how early the melting starts in the spring. So if the melting starts in March and goes through September, we're going to lose a lot of snow. If the melting starts July 1 and goes through September, that's not a very long time period of warm temperatures to melt that snow. So I think there's an influence of keeping the snowfall going into the spring, but I think it's probably just shortening that melting season, causing the glaciers to grow. All right, we do have on-the-ground observations of those 3 wet spring years. So this is September of 11, 2010. Really? No, it should be 11. Sorry. And what we can see is, what we can't see there is we can't see that bare ice. Right? The bare ice isn't showing. We can find a little bit around the edges in this was Labor Day weekend, so early September, not quite to the end of the melting season. But this might be the snow from the year before. This is that year's snow, and it hasn't all melted away. So we can observe that the snow isn't all melting away. That means that the glacier has to be gaining ice mass in the form of snow during that time. So that's, if we want healthy glaciers, all we have to do is hope for rain and cool weather through June. And none of this sunniness like we have out there now. It's great for us, and maybe not so great for the glaciers. So I'll stop there. I've gone through all this, and I do want to say there are things that we need to do. We need better weather records. We need weather stations at high elevations. It's very important to get to understand these things better. It's better to know what the weather is like up there rather than down here. So we need better weather stations. We need better analysis, more in-depth analysis of the long weather records. And then every year these things should be photographed. And the park is starting to keep closer tabs on these things. The climbing rangers are taking photographs from specific places at specific times, which should help document these things. And then just aerial flyovers is the way that glaciers are monitored in many places. And then the best way to do it, the coin of the realm in terms of glacier studies, is to go out and measure the snowfall at the end of the winter, measure how much of it melts during the summer, and actually get a series of on-the-ground measurements, and it makes a lot of sense for these glaciers. So hopefully over the next few years, the park and maybe we will get more of this going. All right, lots of people to thank, lots of funding organizations, and the Park Service was very helpful in getting Hazel going in this project, and you can see all the names of people places there. So I'll stop right there, entertain any questions you have, gone over time a little bit. Anybody who needs to leave, don't feel like being taunted or anything like that. If you have questions, please fire away. Yeah.
Obviously, dark dust and stuff on snow makes it melt faster. So, like, the cars were blowing around the air, or like Mount St. Helens, you rush, has there been anything much that is for especially the glacier area,
Right.
that would make it melt too.
Right. So the question is, would darker dust getting on the glaciers cause melt faster? The answer is absolutely. And there's and it's because it absorbs the sun's heat right onto the snow where it really counts in terms of melting it. And there's a whole field of study on black carbon on glaciers, soot especially, but also rock dust. And would it affect these glaciers? I think it would. I think a lot of the dust from the Snake River Plain, which would be the biggest concern, I think, for these glaciers, I think it gets captured down in the Teton Valley, probably the Big Hole Mountains, and some of the other ranges a little bit to the west capture a lot of that. And the Schoolroom Glacier, definitely some dirt in that photograph, some dust on there, but it's not a lot. And it would have an effect, but it doesn't seem to be having a lot of effect. Rockfall, dark rocks falling on the glacier would certainly have an effect until it gets about that thick and then it comes away. So, yeah, go ahead.
You mentioned something about how long it takes a Schoolroom Glacier to, is that an actual glacier? Is it going to take from the top to the bottom?
It's an